All right, let's talk about concentration. So I don't know about you, but I grew up with this orange juice. It's frozen and it's in the freezer aisle, and it comes in this little can, and you take this thing and you dump it in another container, usually microwave it for a little bit. I gotta put the dog out. I have a prop that he's really wanting, and you guys will see it in a second. Okay, so you put in that container and you fill it. You add about 3 or 4 cans of water. 3 if you're normal, 4 if you're my frugal parents. And you mix it all together and you have something that resembles orange juice. Some of you may have had this before, and this is called concentrate. It's called concentrate because it's highly concentrated. What does concentration mean? Well, it's the amount of stuff in something. It's the real scientific definition. It's the amount of stuff in something. So if you have something that's a high concentration, there's a lot of stuff in there. The CO2 concentration in the atmosphere is increasing, meaning the amount of carbon dioxide in the atmosphere is getting bigger. There's more CO2 in the atmosphere. And alcohol, for example, there's varying amounts of percent of alcohol that might be found. So let's talk about some units of concentration, given that. ppm, parts per million, parts per billion, parts per trillion. You don't really necessarily need to know this yet. You'll get there in Gen Chem, and definitely if you move on in further chemistries. But parts per million is one of them. Oftentimes we talk about things in terms of percent. So if you go and you get yourself an energy drink and it says, hey, this energy drink is 2% juice, you're like, wow, that's so healthy. And yeah, and you drink it. So percent. Another one that y'all would know nothing about because you're all underage. Proof. Proof being essentially double that of percent. So alcohol, vodka, for example, if it's 120 proof, that's 60% alcohol. And of course, we're chemists, so one way that we like to look at the amount of stuff in something is in mole. When we're talking specifically about solutions, that's going to be in mole per liter. Mole per liter is also called molarity, and it's represented with a big M. In fact, you use molarity as concentration in chemistry so much that oftentimes you just say, what's the concentration? And you assume that whoever's looking at it knows you're talking about mole per liter. Okay, before we get too far into this, I'm gonna have one rule. Well, I'm just kidding. I have 2 rules this entire lecture. Rule number 1 is if you see big M, you cross it out and you write mole per liter. That's because it will help you see and separate these 2 things into the amount of moles in a liter. Rule number 2 we'll get to in a little bit. Okay, so question number 1 says, how would you make 1 liter of a 1 mole per liter solution of sodium chloride? Well, think about a soda bottle. In fact, let me go grab one. This is my rad 1 liter bottle. And somebody, how cool are these? Got mold problems? Call Avogadro 602-1023. Yep. Lone pair. Laughing gas. Hee hee hee. Oh, what's this? Is that a goldfish? Yeah. Okay, so I'm over it. This is about a 1 liter bottle. So if I were to make 1 liter of a big M. What do you do with big M? Oh yeah, you cross it out and you write mole per liter. How would I make 1 liter of a 1 mole per liter solution of sodium chloride? Well, you get a liter bottle, which we have, and we want to make 1 mole per liter. In other words, we want to add 1 mole of sodium chloride into here and then fill it to 1 liter. Then we have 1 mole in 1 liter. Just as a reminder, how do we get 1 mole of sodium chloride? You can't count out 6.022 times 10 to the 23rd formula units, but you can consult the periodic table, which will tell you that it has a mass of 58.44 grams per mole. Telling you if you get 58.44 grams of sodium chloride and put it in there, you've just put a mole into your solution. So what you'd really want to do is fill it roughly halfway or a little more. You'd want to add your 58.44 grams, and then you want to fill it up to the 1 liter mark after you've dissolved it. So why you do that is once you add salt, if you remember our conversation from chapter 5 regarding solubility, salt and water love each other, the volume will actually go down a little bit once you've added that in, and then you fill to 1 liter. All right, so that is how. How many moles are in 2.1 liters of a 4.2 mole per liter solution of calcium bromide? All right, first things first, big M, we change that to mole per liter. Now here's rule number 2. First rule is turn that to mole per liter. Rule number 2 is this: when you have a volume of A, we're going to multiply those two things together. We're going to multiply them together. First, let's go ahead and draw it out, and so we have an idea of what this question's even asking. It's saying you got 2.1 liters, so let's go ahead and do 2.1. And this little one over here. So you got 2.1 liters, and each of these liters has 4.2 mole. And this has a little less. Now actually you could look at it and say it's got 0.42 mole because it's 1/10 of a liter. But if that doesn't come intuitively, just know it's a little bit less. The reason I do this is so we can automatically guess what our answer should be. It looks to me like it's going to be about 8.5, almost 9 moles. Because we got 4.2 plus 4.2 plus that little bit there. So you know it's going to be at least 8.4 moles. All right, but now let's see why we do this calculation. Again, rule number 1 is change that to mole per liter. So let me write that down. Rules. Number 1, big M becomes mole per liter. Rule 2, when you have a liter times mole per liter, I already gave you that, liter of A, mole per liter, multiply them together to get moles. Let me show you how that works. We have 2.1 liters of a 4.2 mole per liter solution. If we were doing dimensional analysis, if this is liters, what has to go down here? Has to be liters. What's left up top? 4.2 mole. So 2.1 liters times 4.2 mole per liter. The liters cancel. Let's go ahead and calculate it out. 2.1 times 4.2 gives me 8.82. Or we'll use sig figs, 8.8 mole. So anytime you see liters of A or of mole per liter solution, you multiply those things together to get moles, just like when you turn grams into moles. All right, let's look at another example. It says how many mole are in 455 milliliters? It's 0.455 liters. I would just get in the habit of moving, anytime you have milliliters, moving the decimal place 3 times. Ooh, of a 3.0 mole per liter solution. We change this to mole per liter. And now we've got 0.455 times 3. So let me show this, 0.455 liters. And I said, hey, I know that I've got of a, you can multiply it together right there, or you can draw it out. And there, a liter, there are 3.0 mole. And I get an answer of 2 sig figs, 1.4 mole. And that should make sense because you have about half of a liter, so you know there's 3 moles in a liter, so you should have about half of a mole. Now, why did I go blah, 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 and put whatever here? Because it doesn't matter what we're talking about. When I go to write your exams, I always make sure I include something here, a calculation multiple choice, where I've just randomly thrown in the molar mass of this somehow, in case you think that the molar mass here matters. It doesn't. We're asking you to take liters and mole per liter to figure out moles. Doesn't matter if we're talking about sodium bromide, calcium chloride, sodium chloride, any solution whatsoever, any aqueous solution. The concept is always going to be the same. You got liters, you got mole per liter, you multiply together to get moles. I'm going to say that again. You have liters, you have mole per liter, you multiply them together to get moles every time. All right. Okay, let's kind of go backwards a little bit. Now it says what volume of 1.6 mole per liter HCl contains 0.56 moles. Well, let's talk about it logistically. If you have a liter of a solution of HCl and it's got 1.6 mole in it, the question is how much of this has 0.56 mole? Well, it looks to me like about a third of it would have 0.56 mole, because in this whole liter there's 1.6 mole and we're looking for only 0.56 mole, about a third. But this is not liters of a mole per liter solution. We're not multiplying things together. In fact, you have moles in mole per liter. But dimensional analysis still applies. Let's start with what we know. We know we've got 0.56 mole. And we know that there are 1.6 mole in a liter. It's asking for volume. So our moles cancel, we're left with liters. That's a unit of volume. And I get 0.35 mole as my answer. All right, let's talk about donuts. This is why my dog is freaking out. I usually discuss donuts before this next section because when I drink coffee sometimes, as I am right now, when I drink coffee sometimes, my kids put random stuff in my coffee. I've had cars in there, certain amounts of trash, just lovely things that kids love to do when they're running around your coffee. And so one time my daughter put a donut in my coffee, and you don't even know sometimes until you get to the bottom and you're like, what just happened? So let's talk about donuts. If this is a cup, and this is a dog toy, so if this is a cup of coffee, and let's say I'm drinking it, and my toddler comes over and takes 2 donuts and dissolves my 2 donuts in my coffee, now my concentration of donuts per cup is I have 2 donuts per cup of coffee. Now let me go ahead and make that a little more visual over here. If this is my coffee cup, I have 2 donuts in it now. Now, let's say I were to take this solution and pour half of it into another container. So I took my 2 donuts per cup and I poured half of it into here. Well, now I've poured 1 donut in, but what's my volume? Here it was 1 cup. Now over here it's going to be half a cup, right? So my concentration over here is 1 donut per half a cup, which if you take 1 divided by 1/2 is still 2 donuts per cup. Changing containers did not change my concentration in any way, shape, or form. Just like if you got 100 proof vodka, and you pour it into a smaller container, that concentration is still 100 proof. You haven't done anything to change the concentration. You have to dilute it in order to do that. I'm gonna go give my dog this toy because he's dying. Hey, you wanna come with me? Yeah, you do. Come on. Let's go for a walk, class. Okay, dude. Aren't you so excited? That squeaked. Are you so excited? What about this one? Okay. Did you get all those in your mouth? No. Thanks, Cordy, for your patience. He was really not very patient. Okay. He's been waiting for months because I got that several months ago. All right, so it doesn't matter if we've got 2 donuts per cup or 1 donut per half a cup. It's still the same concentration no matter what you do. It's not until you add something to it that it actually affects it. So let's go ahead and say we've got our 1 donut over here in a half a cup. And then we add water to the 1 cup line. Well, now we have 1 donut per 1 cup, which would be 1 donut per cup. And so we've effectively reduced our concentration. The only way we could reduce our concentration is by adding water. And that should make sense that we reduced concentration because remember, concentration is the amount of stuff in something. Now we have less stuff. It's less spread out than it's more spread out here than it was here. Here was more concentrated. There's more of it in a smaller amount of volume. Now there's the same amount in a bigger volume, lower concentration. Okay, so how this might show up on an exam. It says you pour exactly half of a solution of 0.84 mole per liter NaBr into a beaker. What is the concentration? Well, you've got 0.84 mole per liter. You don't know how much of this you had. You pour half of it into another container. And what is the concentration? Well, just like if we pour anything into another container, the concentration is still the same. The answer is 0.84 mole per liter. I guarantee you that question will show up on a test. Okay. Now it says you pour 240 milliliters or 0.24 liters. Remember, you want to move the decimal place 1, 2, 3 times. This thing only had 2 significant figures. Ooh, of a 1.6 mole per liter solution, what do we do with of a? We multiply it together. In other words, we now have, before we even begin this problem, we now know that this is talking about 0.24 times 1.6. This is talking about 0.384 moles. And then it says you fill the beaker to 500 milliliters. Well, let's go ahead and draw this out. You've got some kind of beaker. In that beaker, you start off with 0.384 mole. And originally you had 0.24 liters. This is 0.500 liters. So you take that 0.384 mole and you fill it to 0.500 liters. What is the new concentration? Again, I said oftentimes they'll just say concentration and they assume that you know they're talking about mole per liter. So the ultimate question is, in this beaker, do we know how many moles we have? Yeah, we've got the 0.384. Did adding water affect the number of moles that were in there? No, just like adding water wouldn't affect the number of donuts in my coffee. So we know we have this many moles. Do we know our volume? Yeah, our volume is 0.500 liters. This 0.384 only had 2 sig figs because it's 1.6 and this had only 2 sig figs. So our new concentration is 0.384 divided by 0.500. And I get an answer of 0. That just doesn't work out. Oh, yeah, no, that's great. 0.384 divided by 0.5, 0.77 mole. Again, I'm sorry this is raw, but I do expect you guys to be doing this with me. Mole per liter. So 0.77 mole per liter. Let's ask if that answer even makes sense. Well, we started off at 1.6 mole per liter, if you remember. It was relatively concentrated. Then we doubled, almost more than doubled the volume, which means we should about half the concentration. So the concentration does, in fact, make sense. If you're doing these problems and somehow you get a concentration that's higher after adding water, you know something went wrong. All right, let's look at this next example. You pour 240 milliliters, or 0.24 liters, of a times 1.6 mole per liter solution. Let's go ahead and do that again. My dog's squeaking. 0.384 mole with 2 sig figs into a beaker and add 500 milliliters. Well, let's talk about the difference in language here. In this case, we got 0.384 and there's 0.24 liters. And now it said we add. Here we filled 2. Here we're adding 500. The difference between filling to a certain volume and adding is one you fill to and the other one you add. In this case, we're adding 500 milliliters. So that's 500 milliliters, 0.500 liters. We add to this of water, giving us a final volume of 0.74 liters. 0.24 plus 0.5 gives us 0.74. So now, when we go to figure out our concentration, which is in mole per liter, we again just ask the same question. How many moles are in there? 0.384. How many liters? 0.74. So we take 0.384 divided by 0.74, and I get 0.52 mole per liter. And that should make a lot of sense because it should be less concentrated than this one, because in this one we added less water. This one we only added 260 milliliters. Here we added 500 milliliters, so a lot more water. Make sure you know the difference between these two things. Make sure you understand the difference between the fill to and the add. Those are very important. All right, now would be a great time for you to take a break if you're having trouble following, or I would do this on a second day altogether. Because now we're pulling earlier chapter 6 stuff with stoichiometry together, and it's going to be fun. This is the last of the semester, y'all. Okay, so you react 0.85 milliliters, 0.085 liters of a 1.1 mole per liter solution times 1.1 mole per liter of silver nitrate. So I'm just going to go ahead and multiply those together. 0.085 times 1.1 gives me an answer of 0.0935. Mole. With 65 milliliters, that's 0.065 liters of a 1.2, so times 1.2 mole per liter. 0.065 times 1.2. We get an answer of 0.078. Mole calcium bromide. It says how many mole of precipitate can you make? In other words, what is your theoretical yield of precipitate? All right, this is no different than what we've already done, with the exception of at first we had liters and mole per liter, so we multiplied them together. Now we've got moles. Let's go ahead and write each one down here. We got 0.0935 mole of silver nitrate. We got 0.078 mole of calcium bromide. It says how many mole of precipitate? Precipitate would be the solid over here. It's asking about this one. Can you make, or what's your theoretical yield? Step is the same as always. We have to remember the limiting reactant. Oftentimes you'll look at this and you'll just use one. Don't forget, the process is still the same. Just because we had this extra small step doesn't mean the process changes. We divide this by 2, we divide this by 1, we ask which one's smaller. This one's smaller. This is my limiting reactant. To figure out how much silver bromide I have, I say, okay, I got 0.0935 mole of silver nitrate. I know for every 2 mole of silver nitrate, I get 2 mole of silver bromide. In other words, 0.0935 or 0.094 mole of silver bromide is my theoretical yield. Now it says, if you collected 14.1 grams of precipitate, what is your percent yield? Well, again, the precipitate is the solid, right? That's our silver bromide. This is our precipitate. If we made 14.1 grams of it, what do we do with grams? Put it into moles. Divide this by 187.77 grams. So let's do that. 14.1 divided by 187.77 gives me an answer of 14.1 divided by gives me an answer 0.0751 mole. 0.0751 mole. And now it says, what is your percent yield? Well, it says you collected. That means you actually got this many mole of precipitate. Remember, percent yield is actual over theoretical. Our actual yield is 0.0751 mole of silver bromide. Our theoretical is 0.094 mole of silver bromide. Now we just take one divided by the other times 100%. Sorry, I forgot the times 100% down here. And we get 0.0751 divided by 0.094 times 100. And I get an answer of 79.9%, which with 2 sig figs would be 80%. All right, so this kind of brings everything together all semester. I've got one more, I think, challenge question for you guys. And let's go ahead and get started. All right, so it says potassium carbonate. We should recognize potassium carbonate as K2CO3. And aqueous, iron 3 chloride. I say aqueous in case you didn't know it was aqueous. That's Fe2. Oh, just kidding. That's FeClO3. Because iron has a 3+ charge, chlorate's got a -1 charge. Reactant and double displacement. Well, if we have potassium carbonate reacting with iron 3 carbonate, or iron 3 chlorate, and a double displacement, we're going to form potassium chlorate, which should be soluble because potassium's soluble, and iron 3 carbonate, which would be Fe2CO3. If we went through and assigned the phases to each of these, this one's aqueous with the potassium. This one's aqueous because I told you it was. This one's aqueous because potassium, and this one is solid because carbonates are solid under specific conditions. They have very minimal exceptions. Okay, so let's balance this reaction. as I go through and look at some things, I see potassium, I got 2, I put a 2 there, but then I eventually have 3 chlorides here. So I've got, if I put a 2 here, I've got 2 chlorides here. So I want to make sure that I have the appropriate number, and anytime I have a 2 and a 3, I should be thinking 6s. So let me move on to the next one. If I change that, then I'm going to change iron over here. I got 2 irons over here, I got 1 iron. Iron actually looks like a good spot to change, because if I change iron over here to give it 2 and 2, then all of a sudden I have 6 chlorates, right? And I know that I was going to be working with 6 as soon as I had a discrepancy of a 2 and a 3. So over here I've got 6 chlorates. I'm going to put a 6 there. Now I've got 6 potassiums. I've altered the number of potassiums, so I need to put a 3 here. Now I got 3 carbonates. That's cool because I got 3 carbonates over here, and my reaction has been balanced. So it's 3 K2CO3 plus 2 Fe, and then you got 3 chlorates in parentheses, yielding 6 potassium chlorates and 1 iron 3 carbonate. Change pens. Okay, now it says what volume of 0.55 mole per liter potassium carbonate is needed to fully react with 0.135 liters of A times 1.5 mole per liter solution, iron 3 chlorate. So you're going to multiply those together. 0.135 times 1.5 equals 0.2025 mole of iron 3 chlorate. So now let's go ahead and change this question. It says what volume of 0.55 mole per liter potassium carbonate is needed to fully react with 0.2025 mole of this iron 3 chlorate. I'm going to rewrite this reaction down here so we can answer this problem a little more efficiently. So I want to leave a little more space for it so we can see it more clearly than I drew it up there. Okay, so if I go through and read this question again, it's asking about potassium carbonate. We really don't know how much potassium carbonate we have, but it says how much is needed to fully react with this 0.2025 mole of iron chlorate. Well, it's essential stoichiometry. If we have this many mole of iron chlorate, we can figure out how many mole of this we need. Because if we had 2 mole of iron chlorate, we need 3 mole of this potassium carbonate, right? So I'm going to say that again. If we have 2 mole of iron chlorate, we need 3 mole of potassium carbonate. But we don't have 2 mole, we got 0.2, so we should be expecting about 0.3 over here. Let's go ahead and figure out how many moles of this we need, and then we can use what we now know about solutions to figure out how much volume we need. We got 0.2025 mole of iron chlorate. We know for every 2 mole of iron chlorate, iron 3 chlorate, we get 3 mole of potassium carbonate. So I'm going to take my original answer, divide it by 2 times 3, and I get an answer of 0.3038 mole of this. So we need 0.3038 mole. If you look at how we did this earlier, I gave a question very similar to this. I said you've got this many moles of something, what volume do you need to have that many moles? So our question is, what volume of 0.55 do we need to get this many moles? Remember, big M is mole per liter. Should have done that right away. So now our problem becomes, I can't wait to have my office back, you guys. Now our problem becomes 0.3038 mole of potassium carbonate And we know that there are 0.55 mole in a liter of potassium carbonate. And I get an answer of 0.552 liters. 0.3038 divided by 0.55, 0.552 liters, or 0.55. In other words, for this reaction to happen, you need 0.55 liters of 0.55 mole per liter solution, and you'll end up getting the correct amount to react with this 0.2025 moles. All right, let's move on. It says if 28 grams of iron 3 carbonate is collected, what do we do with grams? Oh yeah, we turn it into moles, divided by 291.72 grams per mole. 28 divided by 291.72 gives me an answer of 0.0960 mole of iron 3 carbonate is collected, and now it's asking for the percent yield. Well, we know that percent yield is actual over theoretical times 100%. Do we know our actual? Oh yeah, we do. Our actual is 0.096 mole of iron 3 carbonate. Our theoretical, we can figure out. In fact, I'm going to get another piece of paper to do that. I didn't leave enough space. I'm sorry for that. Hopefully you have some more because you didn't do landscape. All right, so our theoretical is we just have to look for our limiting reactant. Because they're both the same, it should be equal amounts, so we could choose either of these to be our limiting reactant. So for example, if you divide this by 2, you divide that by 3, you should get the same number. So you can choose either one. I'm gonna go with the iron because I like to use, I don't know, it looks easy. So we're gonna say 0.2025 mole of iron chloride. I know, and again, we're looking for the theoretical yield. I know for every 2 mole of that, I get, I'm looking at this guy over here, 1 mole of the iron 3 carbonate. So let's go ahead and do that. 0.2025 divided by 2 gives me an answer of 0.101 mole. And again, that's my theoretical. So now I can go back here and say, okay, in actuality, I should have, I got 0.0960 based on the grams here. But in theory, I should have gotten 0.101 mole Fe2 CO3 3. You multiply that by 100%. And you get an answer of 94.8%. or 95% yield. Pretty good yield. Good job. Okay, so to reiterate, we went through here. First, we had to know compound names. Then we had to balance the reaction. Then we had to use that balanced reaction to figure out the rest of the information. So here it gave us moles and moles per liter, so we had to know that we had to multiply those two together to get moles. We had to use our theoretical yield information to figure out, in theory, how much should actually be able to react. And we had to use our newfound knowledge about actual yield and percent yield to figure it out as well. So this question right here encompasses almost everything you've learned, and including even turning grams into moles. This question encompasses everything you've learned the entire semester. If you can do this question and you can understand this question, then you ought to be feeling pretty darn good about yourself. And I don't mean doing it in terms of just going through it. I mean, can you take a paper, turn it over, write what the question was from scratch, know each step of the way, and understand why you're doing what you're doing. When you get to that place, then you should pat yourself on the back for having a wonderful semester. I'm gonna miss y'all. And yeah, have a good one. Bye.